Imagine a quiet spacecraft floating in darkness. Panels sleep. Instruments hum like distant crickets. Outside, stars hang in their usual patience. You place a hand on the console and nudge the engine. Not much, just enough to begin a long, steady push. The ship drifts, then glides, then runs a little faster through the dark. You keep your breathing slow. You listen to the soft vibration of structure and current. You watch a single clock on the wall, ticking like a heartbeat. Here is the gentle thought that guides the journey. If you fly near the speed of light, the world does not simply rush by. It changes its shape in the way it meets you. Time folds. Distance shortens along your path. Colors slide. The sky ahead gathers itself into a bright cone, while the world behind fades and reddens like a sunset that does not end. To you, inside the ship, your pulse is steady, your tea still steams, and your music keeps its tempo. To someone watching from far away, your heartbeat seems slow, your music stretched. Both stories are true inside their own frames. At the heart of this quiet strangeness sits a simple rule. Light has one speed in empty space. Not sometimes. Always. Your ship can hurry as much as you like, but light will not yield you its lead. This was the seed in Einstein's mind, a seed that grew into special relativity. From it grew consequences that sound like magic, yet settle into reason when you sit with them. If light's speed is the same for every observer, then time and space must bend to protect that sameness. Clocks do not agree in the old way. Rulers pointed along your motion do not keep their length in the old way. The universe keeps the speed of light steady by letting time and space be supple. Let us ease into a picture. You shine a little light clock inside your cabin. It is just two mirrors facing each other, a photon bouncing back and forth between them. Ping, ping, ping. Every bounce is a tick. If you are at rest, the photon goes straight up and down. Now let the whole device slide past a window where a friend watches. To them, the photon still travels at the same speed, but it must trace a diagonal path, up and forward, then down and forward, like a tiny zigzag. A diagonal path is longer than a straight one. If light's speed cannot change, then the ticks must take longer. Your moving clock runs slow to your friend's eyes, not broken, not confused. Just part of a new agreement that space and time make with each other. You may smile at that. A little light clock. A little zigzag. But this is not a trick of drawings. Muons made high in the atmosphere live longer when they rush toward the ground. Their internal clocks are slow compared to ours, so more of them reach detectors than classical lifespans would allow. The satellites that guide your maps and your walks carry clocks corrected for their speed in orbit and their height in Earth's gravity. GPS would drift and fail if we ignored these effects. Relativity is not only a poem, it is a tool we keep in our pocket. Back in the cabin, you fold the harness away and float for a moment. The engine hum deepens. You watch the stars. At first, they look ordinary. Then very slowly, the sky begins to lean forward. The constellations stretch and tilt when you are not looking. Light from ahead narrows into a smaller patch of sky. This is aberration. Your motion re-aims the arriving starlight, the way raindrops seem to slant toward you when you ride a bicycle. It is not a violent change, more like a long, slow exhale. The front window grows crowded. The back window grows empty. Later, you notice the colors beginning to slide. Starlight from ahead becomes a little bluer. From behind, a little redder. This is the Doppler shift, a change in wavelength tied to motion. Sound does this when an ambulance passes. Light does it too. Near light speed, the effect grows. The blue shift ahead becomes startling. The red shift behind deepens into darkness. You have not altered the stars. You have altered the relation between you and their light. A quiet thought settles. If your clock ticks slow to others, what happens to the trip itself, measured by you? Imagine a far star, 4 light years away in Earth's frame. If you could cruise at a speed very close to light, 2 sure things happen at once. To people at home, the voyage takes a little over 4 years. To you, the distance in front of you contracts along your direction of travel. It shrinks by a factor that depends on how fast you go. The trip, in your time, takes less than 4 years. Time and distance work together to keep light speed faithful. No one cheats. Everyone keeps a different record. You reach to the console and dim the lights to a midnight glow. A small plant by the window turns its leaves toward a diode. You feel the hush of isolation outside and the warmth of your microclimate within. You are a small pocket of normalcy, skimming the edge of an extraordinary regime. What exactly will the sky look like as the speed grows? How will the cabin feel as your hours drift away from those back home? What happens to energy, to mass, to the simple act of sending a hello to Earth and waiting for a reply? Let the engine keep its steady push. We will take this journey patiently. With each gentle increase, the universe will show one more layer of its soft geometry. Ahead, the sky will gather into a cone of blue. Behind, the night will fall away like a curtain. Between your pulses, years might unfold elsewhere. It sounds like a spell. It is just the world keeping an honest promise to light. Before you race forward, it helps to sit with the rules. Special relativity begins with 2 calm statements. The laws of physics are the same in every inertial frame, which means for every observer who is not accelerating. And light in vacuum has the same speed for all such observers. These are not loud claims. They are quiet stipulations about fairness and rhythm. From them, a new geometry rises, one where time and distance cooperate to keep light steady. Old intuition says speeds add the simple way. If you walk inside a train, someone at the station should see your speed as the sum of yours and the train's. For small speeds, that is fine. For near light speed, nature chooses a new recipe. Velocities do not stack beyond light's limit. If something moves at speed u inside a ship sliding at speed v, the speed seen from the outside is not u plus v. It is u plus v divided by 1 plus uv divided by c squared. No matter what numbers you choose below c, the result nestles under c. This is the way the cosmos keeps its brightest messenger from being outpaced. Let us return to the light clock. Its diagonal path to the outside observer gives a time dilation factor with a simple shape. Gamma is 1 over the square root of 1 minus v squared divided by c squared. That number tells you how much slower your moving clock appears. At half the speed of light, gamma is about 1.15. At 0.8 c, gamma is about 1.67. At 0.9 c, about 2.29. At 0.7.09, gamma does not explode all at once. It swells steadily, then steeply, as you press nearer to light speed. Multiply someone's proper time by gamma to see how long it seems to you while they move. Divide your own aboard time by gamma to see how short it seems to you compared to those at rest far away. Length contraction shares the same factor. A ruler aligned with your motion is measured shorter by others watching you run past. In your own frame, your ruler is normal. It is the world ahead that contracts. Distances along your course shrink by a factor of 1 over gamma. To Earth, Alpha Centauri sits about 4.37 light-years away. To a ship coasting at 0.99 c, the distance along the line of travel is about 4.37 divided by 7.09, near 0.62 light-years. At that speed, the trip in shipboard time would be about 0.62 years, around 7.5 months. You will arrive before your next birthday, while those at home mark more than 4 years. Keep your breath slow. These effects are not optical illusions. They are not tricks of late light arrival. They are relationships written into space-time itself. Yet there is another layer about what your eyes actually see. Light takes time to reach you. Fast motion turns that delay into an artist, repainting what is visible. Straight rods angled to your motion may appear rotated, a Penrose-Terrell effect that makes spheres look like spheres, even when their lengths are contracted in coordinates. The world is generous enough to be both geometric and optical at once. How did we come to trust these quiet rules? The steps were small and careful. The Michelson-Morley interferometer in the late 1800s tried to detect Earth's motion through a supposed ether by comparing the time light took along 2 perpendicular arms. No shift appeared as the device turned. Light's speed seemed stubbornly constant. Einstein imagined a world without the ether and kept the constancy as a postulate. Mathematicians like Lorentz and Minkowski provided the transformations and the geometry that make time a partner to space. The equations were tested in particle beams, in cosmic ray showers, in precise atomic clocks flown on airplanes. Everywhere, the same soft verdict. Clocks in motion run slow relative to the ones you call at rest. Distances along the motion shrink. Simultaneity becomes a local story, not a universal decree. Simultaneity is worth a pause. In everyday life, we treat now as shared. In relativity, now spreads differently for different observers in motion relative to each other. Events that are simultaneous for you are not simultaneous for someone rushing past. This is not a paradox. It is a new bookkeeping for cause and effect that still protects the order of things that can influence each other. Light cones define what can reach what. Inside those cones, communication and influence are possible. Outside them, events are elsewhere, unconnected. The speed of light is the seam that holds these cones together. Step back to your ship. As the speed grows, fuel does not make you heavier in the old sense. The phrase relativistic mass is old language that leads to confusion. Better to say this. Your momentum grows more steeply with speed. Your kinetic energy grows without bound as your speed approaches light. Each nudge from the engine adds more energy while giving less extra speed. You can get arbitrarily close to C with enough energy. You cannot touch it. No matter how long you push, C stays a horizon. What will you feel on board as gamma grows? Nothing special at your own pace. Your heart does not struggle. Your T does not hesitate. The strange part is not inside your body. It is in how your world line threads through space-time compared to others. Your proper time is simply the time your clock reads as you go. It is the length of your path in the geometry that includes time with space. Travel near light speed, and your path can be shorter in proper time than the stationary path of your twin at home. The twin paradox will meet us soon, but it is less a paradox than a comparison of paths. Different routes, different lengths, different amounts of life lived. You push your palm against the wall to float back toward the window. Outside, the stars do not blink. They stand in their centuries. Yet the way they meet your gaze evolves hour by hour as your speed rises. Ahead, the light grows bright and slightly concentrated. Behind, it thins. Somewhere between, a ring along the side windows, the colors still look familiar. The ship is not only moving through space, it is moving through a different sharing of time. You can feel the thought becoming comfortable. You will not rush it. In the next breath, we will let the eyes lead, and the sky will teach you what speed does to sight. You turn off a few more lights in the cabin. Darkness deepens. The forward window becomes a theater for subtle lessons. As your speed draws near to the high decimals, the stars begin to migrate. Points that were wide across the front now gather closer to the center. This is aberration. At 0.8 C, most of the sky squeezes into a forward cone with an opening angle of about 70 degrees. At 0.99 C, the cone narrows to about 27 degrees. At 0.99 C, it squeezes to about 8 degrees. The exact numbers depend on the cosine of the aberration, but the feel is simple. The universe ahead crowds forward. The universe behind empties. Color follows position. The relativistic Doppler shift gives each incoming photon a new wavelength according to a calm ratio. For light arriving from straight ahead, the shift factor is K, equal to the square root of 1 plus beta divided by 1 minus beta. Beta is your speed as a fraction of light. At 0.8 C, K is about 3. A blue star ahead becomes 3 times as energetic in frequency and 1/3 the wavelength. At 0.99 C, K is about 14. At 0.999 C, near 45. At 0.9999 C, about 141. The sky in front does not only look brighter, it becomes hotter in the language of light. The same shift works in reverse behind you. The light stretches. Colors warm toward red then slide out of sight into infrared, then microwaves. Familiar constellations fall silent in the rear window. They have not gone. Their light no longer lands in the range your eyes and sensors tuned for visible images can register without adjustment. You can choose instruments that listen to the stretched light. You can ride with a multi-wavelength awareness and keep the sky whole. Or you can let the world simplify. A bright front, a quiet back, a ring where the universe still looks like home. Brightness changes more than you might expect. At high speed, light is not only shifted, it is beamed. Photons that would have arrived from wide angles are redirected into the forward cone, and their arrival rate ticks faster in your time. If an object emits light uniformly in its own rest frame, a traveler sees the forward light boosted by factors that scale with gamma and K in combination. The result is a headlight effect. The stars cluster and intensify in front like rain swept up by a moving car. Behind, a darkness gathers, not empty, but quiet. There is a cosmic blanket in all directions, a glow your eyes cannot usually see. The cosmic microwave background bathes the universe at about 2.7 kelvins. Drift quietly through space, and it is a nest of soft microwaves. Rush forward fast, and the blanket bunches. At 0.8 C, the front warms by the factor K to a temperature near 8 kelvins, still microwave, a little more energetic. At 0.99 C, the front sees near 38 kelvins. At 0.999 C, over 380 kelvins, hotter than boiling water, radiating in the infrared like a stove coil. At still higher speeds, the front could glow in visible light, then ultraviolet, then X-rays, a hazard for any unshielded surface. The universe itself becomes a wind of light, a radiative weather you must respect. Dust and gas, spread thin in interstellar space, become a more tangible wind. A single proton in the interstellar medium, sparse as it seems at 1 per cubic centimeter on average, meets your ship with kinetic energy amplified by gamma. In your frame, these gentle atoms are high-energy particles. At 0.9 C, a proton carries more than twice its rest energy as kinetic energy. At 0.99 C, more than 6 times. To your hull, they arrive as cosmic rays do, capable of ionizing, of stirring cascades of secondary particles. Larger grains are rarer, but carry a stubborn risk. A grain the size of a sand speck is a bullet. A grain the size of dust can pit and erode. Shielding becomes more than a wall. It becomes a strategy. You might carry a cloud of sacrificial gas ahead of you to pre-ionize and deflect. You might deploy layered bumpers that turn larger particles into harmless sprays before they can burrow deeper. You might use magnetic fields to shepherd charged particles away from fragile systems. Even here, the goal is not to frighten. It is to listen to the wind and prepare to sail. Your eyes wander back inside. The clocks on the wall still tick at their native pace. A song still loops around its melody. You ask the ship to ping Earth. The radio stretches your voice into space at light speed. Back home, they receive it red-shifted if you are moving away, blue-shifted if you are coming home. They wait for your words to arrive, and you wait for theirs. The waiting grows, not just because of distance, because of time dilation and the Doppler pause. If you are receding at 0.9 c, every minute you speak may arrive 2 minutes apart by their clocks. If you are approaching, the music of your voice can compress, arriving with a quickened beat. In each case, there is a kind of empathy to be found. You can learn to translate the rhythm between frames. What do planets look like if you pass them at a whisper shy of light speed? There is a strange kindness in the visual world. A fast-traveling camera does not simply see objects squashed along the direction of travel. Because light from the far edge takes longer to reach you than light from the near edge, the image you receive is a composite of different times. Spheres remain spheres to the eye, their features shifted as if they are rotated a little, a Penrose-Terrell effect. A box may look skewed rather than shorter. The coordinate contraction is real in measurements within a frame. The immediate appearance can be counterintuitive and beautiful, a gallery of delayed moments stitched together. Pause again. You have learned what the sky does, what the photons do, what the thin breath of the galaxy does to your hull. You have learned that energy piles up quickly near light speed, that the simple push of the thruster is less and less speed for more and more energy. The question that often arrives now is simple and human. What happens to you and to the people you love if you keep flying? How do your birthdays count? What does it mean to come home when your hours and theirs refuse to match? The next chapter holds a familiar story of twins and a clock, not as a paradox, but as a path you can trace with your finger. Breathe. We will draw it slowly. Two siblings stand on a launch pad at dawn. One climbs the ladder into a sleek craft. The other stays with a thermos and a wave. They smile at each other through helmets and glass. They have done this before in stories. Today, we will walk with them through quiet arithmetic and gentle pictures and see how their calendars unwrap. The traveler accelerates, coasts near light speed, turns around, and glides home. The one on Earth stays, teaches a class, tends a garden, watches seasons pass. When they meet again, both have aged, but not the same. The traveling twin has lived fewer hours. This is not a trick or a contradiction. It is simply that they traced different routes through space-time. And in this geometry, routes have lengths measured in time. Proper time is the time a clock carries inside its own frame. It is the tick count along a world line. For an inertial segment at constant speed, proper time equals the coordinate time divided by gamma. For accelerated segments, the calculation uses the integral of small pieces, each a little proper time. The result is that a path that darts out and back at high gamma racks up less proper time than a path that lingers at rest. If you like a hands-on image, imagine drawing the world lines on graph paper with time vertical and space horizontal. The stay-at-home line is straight and tall. The traveler's line tilts out, then back. In this geometry, the straight tall path has more proper length. There is often a worry about symmetry. From the traveler's point of view during the coasting phases, it seems the Earth is the one moving. Should not the Earth clock run slow? It does during those phases. The resolution lives in the turnaround, and in the relativity of simultaneity. When the traveler changes direction, even gently, the set of distant events that count as now for them shifts. Moments on Earth that were not simultaneous before become included. In a Minkowski diagram, the slanted lines of simultaneity tilt the other way. The traveler's accounting of Earth time jumps forward. No signal jumps. No laws are broken. It is a recalibration of slices through space-time. Add the pieces together, and the Earth twin sees the traveler slow during the whole journey, and the traveler sees Earth slow during the outbound and inbound coasts, with a large catch-up during the turnaround. The final reunion agrees for both. The traveling twin is younger. Run some numbers softly. Alpha Centauri is 4.37 light-years away. Suppose the traveler coasts at 0.99 c after a brief acceleration period, turns around, and comes home. In Earth's frame, ignoring the accelerations for a simple picture, the trip takes about 8.8 years out and back. With gamma near 7.09, the traveler's proper time for the coasting parts is about 8.8 divided by 7.09, near 1.24 years. Add a little for acceleration and deceleration, and the traveler may age around 1.5 years. The sibling on Earth will have aged nearly 9 years. The difference is not a shock. It is the quiet result of gamma. Take a longer reach. The center of our galaxy is about 26,000 light-years away. If a ship could cruise at 0.9999 c, after a long ramp up, gamma would be about 70.7. In Earth's frame, the one-way voyage would take a little over 26,000 years. Aboard, the contracted distance would be about 26,000 divided by 70.7, near 368 light-years. The traveler's proper time for the coast would be near 368 years. With a sustained proper acceleration of 1 gram for a year or two to ramp up and down, the total might still fit inside several human lifetimes aboard. When they return, if they do, the face of the sky would be unrecognizable. Civilizations would have risen and fallen. Forests would have moved. Glaciers would have shifted. The traveler would be a time tourist, visiting the far future by flying fast. There is a tenderness and a somberness to that. It turns relativistic flight into a kind of one-way door through history. You can choose the door if you have the patience and the engineering. The engineering is not small. To sustain 1 gram for a year requires immense energy. The relativistic rocket equation says your mass ratio climbs quickly if you carry reaction mass and throw it out the back. Beamed energy concepts, sails pushed by light, or magnetic scoops have been imagined. Each faces an orchestra of challenges. Radiation, dust impacts, waste heat, guidance over light-year scales. Even here, the point tonight is not to judge feasibility. It is to let you feel the shape of the possible without hurrying past the beauty of the laws. Communication becomes part of the story. If you sail away at 0.9 c, messages you send home arrive, stretched in time and redshifted. Responses arrive to you doubly delayed by distance and by your motion. You can plot signal world lines on the same diagram and watch them cross. There is a new etiquette to conversation at high speed. You speak, then you live a while, then you listen. Coming home, the tempo quickens. Messages blue shift. You may receive years of Earth news in a condensed stream, like flipping through a book quickly, but still catching the story. Hazards hum in the background, but let them hum softly. At 0.99 C, the interstellar medium's protons arrive at you with energies in the JeV range. Shielding can convert their dangerous tracks into showers of softer particles that you catch and calm. A Whipple shield, a thin sacrificial bumper, set far in front of the hull, can vaporize small grains and spread their energy out before it reaches the main body. A forward cloud of gas can act as a buffer. Magnetic fields can bend ionized wind. You would design quiet redundancy. You would accept that the edge of light is a windy ridge, not a quiet cul-de-sac. Now let the twins meet again. The ship lands. The ladder lowers. Helmets come off. One pair of eyes shines out of a face with one set of laugh lines. The other pair of eyes holds a different count. They embrace. There is a catch in the throat for what was missed, and a bright warmth for what is shared. Physics did not make this hard. Time did. And time here is not a ruler god dropped once and left. It is a fabric that spreads differently for different journeys. That is the lesson traveling near light speed carries back. Time is personal and true. Space is flexible and cooperative. Light is constant and kind in its constancy. There is one more horizon to glance toward before we land for the night. What would it mean to live in a universe where such trips are normal? City pairs centuries apart in each other's history. Letters that cross and arrive like autumn leaves. Artifacts launched now and met by descendants who are older than the crew that left. Relativity bends not only physics, but culture. It gives a shape to patience. It gives a rhythm to the idea of home. The engine eases. The stars return to their familiar scatter. The forward cone relaxes. Colors meet in the middle again. You are coasting at a humble pace now, close to the speed of the whisper you thought the universe spoke in when you were a child. The cabin glows with a low light. You float a fingertip over the window and trace the curve of Orion. What did our near light speed journey give us, besides a tour of effects and numbers? It gave a way to think about time that is softer and maybe kinder. We often talk as if there were an invisible clock that the cosmos consults, a universal now that pulls everything along. Relativity replaces that with a field of local rhythms. Each clock keeps its own beat, and the laws promise how these beats compare when paths cross. The promise is exact. It is not cold. It is a recognition that experience has always lived from a point of view. Distance, too, becomes gentler. It is not a fixed wall. It is a stretchable path that shortens when you commit to motion and lengthens when you rest. If your heart longs for distant places, relativity offers a bargain. Go fast enough, and you can make far places near in your own time. The cost is paid in the times of others. You come back younger into a world that has moved on. This is not a curse. It is a character in the story of choice. Some explorers will choose it. Some will choose to stay. Both are part of the human weave. Sight changes most obviously in our thought experiment, And that change carries a quiet metaphor. When you rush forward, the world narrows into a cone. Details ahead sharpen and brighten. The past softens out of sight. Slow down, and the full circle returns. You can move through your days with that awareness. There are times to focus so hard that the future glows and the rest dims. There are times to slow, to let the sides and the rear come back into view, to gather context, to rest in the full sky. The physics sits beneath our lives in more ways than the stars might admit at first glance. Particle accelerators hinge on these same equations. Electrons whirl near light speed and rings and reveal secrets of matter by the light they spill. Muons underground mark time dilation like tiny monks counting beads. Satellites correct for relativity to draw you a path through city streets. Even the color of the sky in your windshield on a highway is a cousin of aberration. Motion changes what meets you, and it always has. Could we one day build a ship that cruises through the interstellar medium with a patient blue cone ahead? The answer lives in engineering more than in physics now. The laws permit. They do not cheer or protest. They are the flat kindness that welcomes any design clever enough to live inside them. Breakthroughs in energy storage, in field control, in materials that heal from impacts, in radiative cooling and waste heat management, in navigation that spans decades, would all be steps toward riding the edge of light for real. Whether we do so is a story the future will write with many hands. As you float, you might remember the quiet failure of the simple sum for speeds, the gentle tilt of simultaneity slices, the way gamma grows like a tide. You might remember the cosmic microwave background, a soft black-body field made to run warm in front by your motion. You might remember that even the visual look of a fast-moving sphere hides a twist in time, a rotated image born from light's own travel time. These are not party tricks. They are the headset nature wears when you ask it to let you go very fast. They are the steadiness underneath the wonder. There is a final comfort in this story. Travel near light speed is a way of going to the future. You do not need a wormhole or a fantasy machine. You need a long, steady push and the willingness to let other clocks race ahead. When you return, you will find tomorrow waiting with more pages filled than yours. You will meet it with the freshness of someone who has kept a different pace. That idea can change how we feel about patience. Perhaps we do not need to hurry everything. Time will do the racing for us if we ask it in the right way. The ship tilts a little, gyros hum. A tiny plant by the window folds a leaf and opens it again. You listen to your own breathing. You remember that even at rest, you are moving through time at 1 second per second, a speed that never needed a fuel tank. You remember that your life is already relativistic, a path through space-time unique to you, crossing and recrossing others with grace. Thank you for flying at the edge of light with me tonight. If this quiet journey left you feeling a little larger, a little calmer, and a little more curious, you are welcome to stay close and subscribe. We will keep wandering gently through the cosmos together, letting science be a lullaby and wonder be our compass.